Thank you. It's a great honor to be here at the Nambu Memorial Symposium. And as you might easily imagine, when I was growing up as a grad student in Japan, of course, Yukawa, Tomonaga were big heroes for me, but as well, the Nambu was an amazing person, giving us a lot of inspiration and encouragement, being in Japan, yet starting to learn about the basics of particle physics and eventually get into research. So it's an amazing opportunity for me to actually be here. And I thank the organizers for actually letting me this opportunity. So what I'd like to talk about is sort of building on something actually Nambu himself did at his late stage in 2002, talking about the Goldstone bosons, Nambu Goldstone bosons, in a context which doesn't have Lorentz invariance. And that's the first subject I'm going to talk about. But I'd like to also add two more subjects. The second one will be about these effective operators, how you actually classify operators beyond any renormalizable field theory. And then possibly, if I have time left, talk about this new speculative idea that the dark matter of the universe could be actually Nambu-Goldstone bosons. So let me get started with the Nambu-Goldstone bosons in systems without Lorentz invariance, which I had worked with in a series of papers with Haruki Watanabe. And of course, I don't need to repeat this, but the concept of spontaneous symmetry breaking was really essential in many of our understandings of the fundamental physics. And at the end of the day, after Nambu's crucial work, it came to this idea that the physics can be described by the geometry of the homogeneous spaces, the coset spaces, and that geometrization of this idea really led to this beautiful story about the whole concept of spontaneous symmetry breaking. And everybody here knows about Goldstone theorem that whenever symmetry breaks, if it's a continuous group G breaking down to H, they are massless bosons with this linear relationship between energy and momentum, which is coming from this matrix element of the current operator between the vacuum and this Nambu-Goldstone boson state. And because of this relationship, there is one Nambu-Goldstone boson for every broken symmetry. And therefore, we have this prediction on the number of degrees of freedom. And this theorem assumes Lorentz invariance and positive definite metric to the Hilbert space. So we all know the Higgs mechanism already violates this because the gauge theory has to either break Lorentz invariance by gauge fixing or give up the positive definite metric of Hilbert space to allow for Lorentz invariant negative metric states to describe the gauge invariance. So that's how we end up with a massive photon or W boson in the Englert-Brout Higgs mechanism. But of course, we have systems where Lorentz invariance may not be manifest, and that examples are the Heisenberg models. And for example, if you take the antiferromagnet with this positive sign here, spin wants to be staggered like this, approximated by the L state, not exact, but nonetheless. And in this case, you have SO3 three-dimensional rotational invariance. But with this configuration, you are only left with this axial rotation, that's SO2. So we have the coset space of S2 with two broken generators. And indeed, we have two Nambu-Goldstone bosons, and the energy goes linearly with momentum. So this seems to still conform to the idea of Goldstone theorem, even though system is not relativistic. But when you go to ferromagnet, though, all the spins are lined up. We still have the same symmetry breaking, SO3 breaking down to SO2 with the two broken generators. But in this case, it has been known for decades that you have only one Nambu-Goldstone boson, and dispersion relation is quadratic instead of linear. So something is not quite applicable based on the original Goldstone theorem to systems like this. And these days, there are more and more systems that exhibit similar behavior. So this is actually a system what my colleague in Berkeley, Dan Stamperkern, realized in his laboratory. So this is the cold atom BEC of spin 1 atoms. It's very confusing that when atomic physicists call something spinor, they mean integer spins, spin 1. But nonetheless, this is a system what they call spinor BEC. So in this case, you have this SO3 cross U1 symmetry to get started with. SO3 for three components of the spin of spin 1 atom, and U1 for the conserved number of the atoms. And therefore, you describe this system using this three-component complex Schrödinger field. So this three-component corresponds to SO3 of spin 1, and each of them are complex, giving you the overall conservation of number by U1 symmetry. And in this system, these three-component fields are quite this weird configuration of expectation values. And this actually breaks this symmetry down to SO2. It's a little difficult to see, so let me actually expand this complex field into the real part and imaginary part into two different columns. And then this expectation value will correspond to 1 for the real component and I for the imaginary component. Then you can see that SO2 or U1 symmetry acts as the rotation between these two columns. SO3 is a rotation among these three rows, and therefore SO2 acting from this side times SO2 acting from that side, diagonal subgroup is indeed unbroken because this looks like an identity matrix. So that's how you know that SO3 equals U1 is broken to SO2. So we have then 3 broken generators. 3 generators there, 1 generator here, 4 altogether, breaking down to 1 unbroken generator, and therefore 3 generators are broken, and coset space turns out to be the real projective space. 3 broken generators, and there's 1 Goldstone boson, Nambu Goldstone boson with linear dispersion, another one with quadratic dispersion, but that's it. You don't have the third Nambu Goldstone boson. So again, the number of broken generators and number of Nambu Goldstone bosons, there's a mismatch. And also, there is this weird dispersion relation. And a lot of urging from myself and Haruki, Dan Steinbergen really did manage to actually measure the dispersion relation of this Nambu Goldstone boson degree of freedom, and it does turn out to be quadratic indeed. So something has to be understood in a more general context. And of course, Heisenberg model has been around for decades, so people did study this question over a long time. And the essential difference between the case of antiferromagnet and ferromagnet turned out to be this. If you take the expectation value of the spin operator along the z direction, in the case of antiferromagnet, they cancel among the neighboring sites, so there is no overall expectation value of it. But in the case of ferromagnet, they all add up. So the Jz has an expectation value. And Jz can, of course, be rewritten as a commutator of Jx and Jy. And this had been pointed out by people in the past. So what this means is that Jx, Jy commutator has a non-zero expectation value. And remember, Jx is an operator that is produced to give this x rotation, which is supposed to give you a Nambu Goldstone degree of freedom. Jy rotation would be another broken symmetry that's supposed to give you yet another Nambu Goldstone boson degree of freedom. But because their commutator doesn't vanish as an expectation value in the ground state, this commutator can be sort of analogous to the canonical commutation relation that two operators don't commute. And in this canonical commutation relation, what we know from a undergraduate physics class is that this means x and p together describe 1 degree of freedom. 1 degree of freedom can be described in terms of its position and its velocity at a given moment in classical mechanics. And in quantum mechanics, of course, they have to be quantized. But nonetheless, x and p together describe 1 degree of freedom. So in a similar fashion, once you have this commutator of the 2 rotation generators to be non-vanishing on a ground state, then this operator and that operator together would describe 1 single degree of freedom, and hence only 1 Nambu Goldstone boson. And at this stage, the connection to this dispersion relation is not completely clear and had been studied. And actually, Subia pointed out this old paper to me that this kind of commutation relation had been known for many decades. But nonetheless, it still doesn't seem to be presented in a very general fashion. So many individual systems have been studied, but the general principle was still not completely clear to most of us. And what we end up doing is to use the language of effective field theory. This particular one corresponds to this ferromagnet, and then identify this canonical structure by looking at this piece in first-order time derivative, and tell you more about this in a moment. So even after these works a long time ago, people still didn't think that there have been a general understanding of what really is going on. For example, back in '76, Niels and Chada actually tried to understand this problem, or how exactly you can understand the number of degrees of freedom and their connection to dispersion relations. And given that in a ferromagnet you had this quadratic dispersion, that's the first part that they focused on. So they classified possible Nambu Goldstone boson degree of freedom depending on what they call type 1, when the dispersion relation is odd power in momentum, versus type 2, when the dispersion relation is even power in momentum. And what they have shown at the end of the day is that compared to the number of broken symmetries, the number of type 1 Nambu-Goldstone bosons plus twice the number of type 2 Nambu-Goldstone bosons has to be equal or greater than the number of broken symmetries. And this they have proven using the analyticity of S matrices. Oops, sorry about that. And indeed, looking at examples we talked about, this inequality does hold. In the case of a ferromagnet, then you have this quadratic dispersion. So we have one type 2 Nambu-Goldstone boson, and 2 times 1 is 2. That equals the number of broken symmetries, SO3 mod SO2, right? So the inequality is saturated. In the case of antiferromagnet, we have linear dispersion, and you have 2 of those. So I have 2 here, and 2 is equals to, again, number of broken symmetries. So again, this is true. And you can also come up with the examples where inequality is not saturated. If you write down this simple U1 theory, and the difference from usual one is that this is actually quadratic in spatial derivatives, so this is 4th power in spatial derivative here, then just by letting this psi field to condense, you do find Nambu-Goldstone boson, and the dispersion relation is even power, so this is type 2. I have only one type 2 Nambu-Goldstone boson here. Twice 1 is 2, which is strictly greater than number of broken symmetries. So then now the Nielsen-Chadha theorem still holds, but as you can see, it's not that constraining. The number of Nambu-Goldstones can be very big compared to the number of broken symmetries in general given by this theorem. So it's not very constraining. So what's still lacking here is that given a set of autoparameters, how do you figure out how many Nambu-Goldstones there are and what their dispersion relations are? Much more recently, in 2001, Schaefer and company and have proven another theorem. Whenever you have this commutator among the generators to all vanish, then you go back to sort of the familiar situation where number of Nambu-Goldstone bosons equals the number of broken symmetries. But again, this is not general enough because this situation is not realized in ferromagnet. And then comes this paper by Nambu, which actually I wasn't aware of until very recently, but this is actually the last physics conversation I had with him back in 2002. So he had this paper, Spontaneous Breaking of Lie and Current Algebras. He talked about these anomalous properties of Nambu-Goldstone bosons. I was very happy to see that he himself wrote Nambu-Goldstone boson in the abstract. But anyway, so here comes the statement about the general Goldstone theorem, but he says there are, however, exceptions to the above theorem, so he wanted to come up with some general understanding of this as well. And this is 2002, and it was followed by also a series of papers, 2002, talking about abnormal number of Nambu-Goldstone bosons, and other papers following in the later years. So this still had been regarded as a puzzle in general. So what we came up with is a general formula. So whenever you have this commutator of the generators with expectation values, this defines an anti-symmetric matrix whose rank, of course, is always even. And half the rank of this matrix is what I define NB, and this basically counts how many these canonically conjugate pairs of generators exist. So namely, what we managed to prove in the end is that whenever you have this kind of non-zero commutator of these generators with the vacuum expectation values in the ground state, each pair, namely half the rank of this matrix, accounts the number of degrees of freedom for those canonically conjugate pairs. But among the number of broken symmetries, if you subtract this rank, that still can leave additional broken generators which don't participate in this antisymmetry matrix. And so we call these guys type B and call them type A. So at the end of the day, the number of Nambu-Goldstone bosons is given in terms of the number of these type A Nambu-Goldstone bosons that don't participate in these commutation relations, plus number of type B Nambu-Goldstone bosons which do participate in these commutation relations. And this is in general different from the number of broken generators because you need to count is 2 of the generators as 1 degree of freedom, so you need to subtract half the rank of this matrix. And this is now the general theorem we proposed, and we managed to prove this using effective field theory. And the connection to dispersion relation also ends up being simple, but actually not straightforward. So these type B Nambu-Goldstone bosons generically have this quadratic dispersion relation, and type A Nambu-Goldstone bosons generically have linear dispersion relations. But I say generically because there are exceptions, and we know exactly when these exceptions also happen. So I come back and mention these exceptions in a moment. But this formula, which we have now proven as a theorem, works in every system people have discussed in the literature where people talked about these anomalies or abnormal number of Nambu-Goldstone bosons. So how does it work? So we just follow the same idea originating from Nambu, Goldstone, and then into Kalan-Coleman Wess-Zumino. So we write the low energy effective Lagrangian using pion fields that live on this coset space. And write the action in such a way that the whole Lagrangian or the action is invariant under the entire group G, not just the unbroken group H. And of course, we expand this action in powers of derivatives and often keep only terms up to the second order in derivatives. And we're all familiar with this result from Kalan-Coleman Wess-Zumino. Then this is the relativistic case. The basic data you need for this purpose is the metric on the coset space. Then you're done. And that's the beauty of this geometric approach to this physics problem. When you go to systems without Lorentz invariance, there is little change on the terms of the two derivatives. The only difference here is that metric relevant for this time derivative piece and metric relevant for this spatial derivative piece can be different from each other now, mostly up to overall normalization, and because there's no Lorentz invariance. But the most important thing is that you can have yet additional term here, which has only the first power in time derivative, which totally changes the counting of degrees of freedom. And this kind of theory had also been known by Yoichiro in earlier works, but this is the basis of our arguments. First of all, what does Lagrangian tell us? So we always expand this first term as well as this metric terms around the origin. And if you expand this term around the origin, the first term is a constant times total derivative in time, so that doesn't do anything, we drop it. What matters is the first order term in this expansion. I have this pi field together with pi dot. So that's the term that's very important for us. Because what that tells you is that you have pi dot as the first term in the Lagrangian, which basically has the form of the PQ dot. So there you identify the canonically conjugate structure between one pion field and another pion field. And so in the subspace where this the matrix, this expansion is invertible, because in general it's not invertible, then that defines this canonical conjugate relationships between the Nambu-Goldstone boson fields. And at the low energies, when they do participate in this matrix here, then this piece here is linear in energy. This piece is quadratic in energy because time derivative, of course, is the energy after quantization. So energy here is actually much more important than the second time derivative, which is energy squared. And also given the fact that you have this term first order in time derivative, definition of the Noether currents is affected, and the lowest order piece actually goes with the pion field itself without any derivatives on it. And then if you compute the commutator between these generators, this is the current, this is the generator after integrating over space, then the simple algebra shows it's nothing but the piece here. Namely that whenever you have this non-zero commutator between different broken generators, that means this coefficient is non-vanishing, and therefore you have this piece in the first order in time derivative. So they're now in one-to-one correspondence. So this commutator between generators really means that you have this first order time in time derivative. And once you do, then you have to balance this piece, which is much more important than that one, which goes with linear energy, has to balance against this piece, which is quadratic in spatial momenta, and therefore you expect this quadratic dispersion, energy should go like momentum squared. And therefore, for these type B Nambu-Goldstone bosons, which participate in this the commutator in the ground state, you would naturally predict that energy should go with quadratic in momentum. But I say this only generically. You can find examples where this expansion in spatial derivative doesn't start with this 2 powers, but may start with higher powers. So even though you have this canonical conjugate structure, you may have energy not going like p squared, but like e to the 4th, for example. Even when you don't have this term, so that pion field doesn't participate in this commutator matrix, then you start with this term that goes like e squared, this term that goes like p squared. You expect this linear dispersion. But again, there could be some specific systems where the first order in the derivative may vanish due to some symmetry reasons. Then this may start again with the spatial derivative to the 4th power. So even when a pion field doesn't have this term here, you may still expect energy squared go like p to the 4th, where dispersion is quadratic. So that's why I said generically. So generically, you do expect that whenever you have this term, namely if the pion field participates in this commutator, you expect energy to go like p squared, but there are exceptions. When the pion field doesn't participate in this commutator, you expect energy squared to go like p squared, and hence linear dispersion, but again, there are exceptions to that. So that's the general conclusion, but when you have this canonical conjugate pairs, you do have one less degree of freedom per pair, and so you have to subtract the half of this, the rank of this matrix. So and physical interpretation of this commutator is the fact that there is a finite charge density in the ground state. So this is the bottom line then. So the spontaneous symmetry breaking originating from Nambu always leads to gapless excitations, namely Nambu-Goldstone bosons. In Lorentz invariant case, the story was simple. The number of Nambu-Goldstone bosons is always the same as number of broken symmetries, and energy always goes linear with momentum. But in systems without Lorentz invariance, you at least have to think about these 2 different possibilities. The type A Nambu-Goldstone boson doesn't participate in this commutator matrix, and typically energy goes linearly with momentum. Type B Nambu-Goldstone bosons participate in this commutator matrix, then typically energy goes quadratically with momentum. And the number of Nambu-Goldstone bosons is the sum of the 2, but the number of broken symmetries is the sum of this type A plus twice the type B. And by writing effective Lagrangian on a previous page, then it not only predicts the dispersion relation and the number of degrees of freedom, but you also know knowledge about the interactions among them. And then we can also try to understand this in terms of geometric language, which was really powerful in the case of Lorentz invariant system. So that's it turns out to be what we call partially symplectic or presymplectic geometry. So the key again is this first term in the Lagrangian. That's the first order time derivative. And this, of course, defines one form on the coset space. And the Lagrangian or action has to be invariant under the full group G, which means the Lagrangian density has to be invariant, possibly up to a surface term. So Lie derivative of this one form has to be given in terms an exact form. And because Lie derivative and exterior derivative commute, if you take the exterior derivative of both sides, then this gives you the actual 2 form whose Lie derivative vanishes because d squared vanishes. What it means is that this coset space not only is endowed with metric, which of course we needed in the relativistic case, but in addition, it's endowed with this additional 2 form, which is a left invariant by the group action. And so this coset space is partially symplectic. The part of the coordinates are these canonical conjugate pairs where the coordinates participate in this sort of like symplectic 2 form. But other parts of the system may not. So this 2 form may be degenerate. And there's a version of Dalbour's theorem that still allows us to write this in canonical form. But the point here is that you have these paired coordinates for the part of the system. You may have unpaired coordinates for the rest of the system. So the coset space is now a very strange space. is partially phase space, partially configuration space. And that's the general situation, it turns out. So this is what mathematicians call presymplectic structure. And after reading several math papers to understand the general idea of the presymplectic structure, it turns out that this is the basic understanding of the geometry. Here's the coset space. In the case of the ferromagnet and antiferromagnet, that's S2. In the case of the spinor BEC, that's RP3, we mentioned that. And then this can be understood in terms of this fiber bundle structure, where the base space is the symplectic homogeneous space. And on this space, of course, because it's symplectic, you have this non-degenerate symplectic 2 form. And what it means is that on this symplectic 2 form translates into this commutator matrix of the generators, as you saw from the analysis of the effective Lagrangian. But this projection would allow you to pull this 2 form back onto this original coset space, and that defines the 2 form on the coset space, which is also G invariant by this construction. But it may be degenerate on it. It's 2 form, but only part of the space can participate in this 2 form because this fiber gets projected out. So all the coordinates on this fiber correspond to these unpaired Goldstone boson fields, and therefore they are type A, and generically you expect this linear dispersion. And all the degrees of freedom on this base space are the type B because they are all paired. You generically expect this quadratic dispersion relation. And so that's the main result. So this number of broken symmetries now, dim G minus dim H, corresponds to the sum of degrees of freedom on this fiber, that's NA, and the degrees of freedom on this base space, they are paired. So each degree of freedom counts twice as a number of symmetries, and then twice NB. So that's how you understand this result from the geometric point of view. And there are many examples of this. For example, if you have the odd-dimensional sphere as UN mod UN minus 1, you can always project it down to CPN, where U1 is the fiber. So you again have the situation that 2n minus 2 coordinates on this one are paired, and they give you type B Goldstone bosons. But additional degree of freedom is not paired and gives you type A number Goldstone boson. So these fields can live on the same coset space due to this structure. So going back to the spinor BEC we talked about before, so you have this RP3 as a coset space, and you can parameterize this 3-component Schrödinger field in this fashion using one complex coordinate z and one real coordinate theta, so that it's now obvious that this coordinate z describes the CP1, that's a base space, 2-dimensional sphere, and theta describes this U1 fiber, so you can describe it this way. And this z describes one type B number Goldstone boson. Indeed, that gives you quadratic dispersion. And theta describes type 1 number Goldstone boson with this linear dispersion. And this projection from RP3 to a CP1 is nothing but the Hopf map. So that's the way things work. And you have seen this dispersion relation experimentally. So that leaves a question about classification. So given a coset space, how many possible pairs are there to build a type B number Goldstone boson? And in the simple case of, let's say, SU3 mod U1 squared, you have 6 broken generators. So using the sum rule we have proven, you can at least think of having 6 type A and no type B, or 4 type A and 2 type B, 2 type A and 2 type B, and no type A and 3 type B. They all add up to 6. But it turns out that this possibility doesn't exist. So you really have to go down and try to classify possibilities. So we resorted to this theorem proven by Chu a long time ago, and also a theorem by Borel. And at the end of the day, you can go through this, and I don't go through details, but you can classify all possibilities that can be realized on a given coset space, which components can be paired into type B, and which components cannot be. And this is the complete list of all possibilities of the group with rank 5, SU6, SO10, and SO11 and SP5 with wonderful duality between them. So that's how you can really classify them. And in addition, once you have an effective field theory, you can learn even more about their interactions. In the case of type A, as we all know from Coleman's theorem, you cannot have a order in one-dimensional quantum system. And that's something you can easily see by the scaling argument that interactions are actually relevant, and therefore that can, in principle, restore the symmetry because of the asymptotic freedom. But in the case of type B, we also know that one-dimensional chain of ferromagnet does break symmetry even in 1D, and that's, again, something you can see from this effective Lagrangian by considering scaling. It turns out that all interactions are irrelevant, and therefore this order, namely the spontaneous broken symmetry, is stable against quantum corrections, and because of this IR-free nature of these interactions. And also, once you have the effective Lagrangian, you can also start thinking about various soliton solutions, and there was an amusing consequence of this. For example, if you have a Heisenberg ferromagnet, again, coset space is S2, and if you have a two-dimensional plane, you can wrap this two-dimensional plane on S2 with the winding numbers, and that gives you the skyrmion solutions. And skyrmion has several moduli, the two moduli in spatial translations, in one in x and y directions. There's a dilation and rotation. And we, of course, can derive effective Lagrange for these moduli once you start with the Lagrangian I have shown you just a few minutes ago. Then there's an interesting result out of this, that translation in x direction and y direction actually don't commute, and the lack of commutation is given in terms of this topological number. And this is very amusing. It's sort of reminiscent of the Witten-Olive anticommutator in extended supersymmetry, where anticommutator of supercharges is given in terms of electrical charges or magnetic charges, these topological charges. It's very much reminiscent of this. And derivation is, again, very simple. You just start out with this Lagrangian I have shown to you before. You canonically quantize it, define this translation generator, and you just go ahead and compute this. And then you go through this. At the end of the day, you find the commutator is a surface term, which we are told to drop in quantum field theory textbook, and therefore momentum operators commute. But in this case, surface term turns out to be exactly the winding number you cannot drop, and hence this kind of central extension of these momentum operators. And to save time, I'm going to skip some of these things. And you can also think about the space-time symmetries. And I skipped just explanation here. But this is one point I wanted to make. If you actually look at the lattice of vortices in a superfluid, you can have a situation where type A Nambu Goldstone boson has this quadratic dispersion. So that's one example, the physical example, where this generic correspondence between the type A and linear dispersion is not true. And the reason is that in this system, the rotation of the system actually shifts this phonon field theta by an amount proportional to x. And therefore, the derivative of x, the derivative of theta still shifts under this rotation, and therefore derivative of theta squared is not allowed by the symmetry. So as a consequence symmetry, you forbid derivative theta squared, so expansion starts with derivative square theta squared, and hence energy squared goes like p to the fourth and quadratic dispersion. So what Niels and Chada did was to focus on dispersion relation and trying to understand this number. But what you can see here is that dispersion relation is a poor measure on how a degree of freedom is related to a broken generator. Because even when you have the standalone generator, then you can still have this quadratic dispersion. But once you understand where this the reduction in number of Goldstone bosons is coming from, then you can you clearly know how the effective Lagrangian works. And you can also identify these exceptional situations where certain terms are missing because of the symmetry, and then you can understand the whole story in a consistent fashion because of that. So to just conclude this part of my talk today, so this has been an age-old subject. Nambu himself worked on it quite recently, but now we clearly understand the geometrical structure behind all of this. The underlying geometry is what they call the presymplectic structure, namely that the coset space is partially phase space, partially configuration space. They can be all mixed up. And once you understand the geometry behind it, you can come up with complete classifications, and you also find some intriguing consequence of that, and I skip the rest. And that moves into the next subject of classification of effective operators. And again, going back to Nambu, there he introduced the four fermion operator, which is a high dimension operator added to renormalizable theory that really changed the dynamics of the theory. And so understanding the consequence of these high dimension operators in general is very important. And phenomenologically, that is even important today. Having discovered the Higgs boson, the standard model is now UV complete, so there's no apparent limit to how far energy the standard model can be applied to. So what we have to do then is to start thinking about the corrections to the standard model Lagrangian coming from the higher dimension operators, which may appear after integrating our supersymmetric particles, extra dimensions, and so forth. Nonetheless, we need to understand in a given field theory what is the complete set of high dimension operators at a given dimension. So this is a very simple question to ask. The minute you have some renormalizable theory, that's the first question you want to ask: what are the possible corrections to that coming from high dimension effective operators? It turned out that this is actually a surprisingly complicated problem. So in the case of the standard model, I think Steven Weinberg was the first one to consider possible high dimension operators to it, and he focused on baryon number violation, lepton number violation back in 1980. And realizing this is an important program, Buchmüller and Wheeler actually tried to come up with a complete set of all dimension 6 operators you can add to the standard model. And they said there were 80 operators when you consider only one generation. But this was actually not correct. And more than 20 years later, finally, people came up with a complete classification of operators. And at the end of the day, there were redundancies among the operators Buchmüller-Wheeler found. And they also discovered one new one. So number 80 became 59. But this was still for one generation. And much more recently, 2013, Anish Manohar and company generalized this to 3 generations, or general number of flavors. And then more other people tried to generalize this further to high dimension operators. But this paper, as you see, turned out to be actually incorrect. So the classifying operators turned out to be a surprisingly complicated problem. And this is the complete set of dimension 6 operators, which I can show you later on. So what is actually the problem? Well, the effective operators are invariants under gauge group, Lorentz group, and so on. And trying to come up with invariants, the theory of invariants go all the way back to Hilbert and Weil. So this part had been all understood. But the problem is that in the field theory, not only that you are trying to write down invariants out of fields, the operators can involve derivatives of fields, and that had not been taken care of by this old theory of invariants. And the minute you have derivatives acting on fields, there are 2 sources of redundancies. One of them is the equation motion. The other one is that different operators may be related by integration by parts. And these things have to be taken care of. So just to give you an example how intricate it can be, just the simplest example I can imagine in 4 dimensions. Just 4-point scalar function at order 2 powers in derivatives. And you can write 10 operators of that type. You have 1, 2, 3, 4 fields here, and 2 derivatives may be acting on 1 field, or 1 on 1 and another 1 on the other one. And there are 10 operators altogether. And out of them, you can immediately see that this operator can be removed from counting, because using equation motion, this turns into mass squared times phi. So this had been already classified at dimension 4 level, so you don't need to count them once more again. So you can remove those, but that still leaves you 6 operators. But we know the answer in this case. This is scalar amplitude. The amplitude can be only proportional to ST or U, Mandelstam variables, at order momentum squared. And we know ST and U have one linear relation, so there can be only 2 independent amplitudes of the type. And indeed, if you pay careful attention to these operators, you can rewrite one operator to another one by using the combination of equation motion and the integration by parts. So you can eliminate 4 out of 6, and you end up with only 2 operators indeed. So already in the simplest example, you can see that things can be rather complicated. And if you think of doing this kind of analysis for all fields in the standard model at higher dimensions, then it becomes a rather intractable problem. And in addition, there are only d linearly independent momenta in d dimensions. If you have 4-dimensional space-time, only up to 4 momenta, they can be linearly independent. But from the 5th one, it's actually linearly dependent on the other 4. You have to also take care of these things as well. So, things can get pretty complicated. No wonder it took more than 20 years to actually get things right. And then our idea is the following. So let's forget about trying to write down the standard model Lagrangian fully, but just focus on the kinetic terms for now. So in the case of the standard model, what practically means is that you just don't think about the Higgs mass term for the moment. If you just focus on these kinetic terms, then this is classically conformal invariant, namely SO4, 2, or we complexify it to SO6. And we take this as a zeroth order Lagrangian, and including the mass term for Higgs, we just try to classify all the other operators we can add to these kinetic terms and try to classify this using the power of this conformal symmetry. And in conformal field theory, there's this operator state correspondence. So classifying operators correspond to basically representation theory of states. And then you know how you can implement these possible two sources of redundancies. The first one is equation motion. And the equation motion for free fields corresponds to the representation of a conformal group of short multiplets where some null states can be removed from the representation. And to remove total derivative operators correspond to just picking up primary states because the descendants correspond to total derivatives. So all you have to do in the end is that by taking this as a starting point, you classify representations of a conformal group and then paying attention to these short multiplets, and in the end, you pick only primary states. So in the end, this is the master formula, and I talk about various factors here, but just to give you the upshot here. So what you do is to take the characters under the conformal symmetry and the gauge symmetries for each field. You take arbitrary power of them in either totally symmetric combination for bosons or totally antisymmetric combination for fermions, and you multiply a whole bunch of them for all possible fields you have in your theory. And then you project that down to gauge invariance by integration over Hauer-Measuring gauge group, and then picking up their primaries by integrating over the conformal group by projecting it by a conformal character of spin 0 field, because it has to be Lorentz invariant, over given mass dimension. So that's what we're going to actually show you in a moment. And I don't think I need to tell you much about Hilbert series to this audience, but this is just a convenient way of encoding all possible operators in a given ring. And you can implement certain ideals. For example, when phi squared vanishes like Grassmann-Ott fields, then this numerator tells you about this ideal. Denominator generates a free ring. And the quotient gives you this just 1 plus phi, telling you that this is the only possible operators when this is Grassmann-Ott. So that's basically a generating function over all operators you have in your system. And you also know about characters. The simple example SU2. And important property here is upon integration over the Hauer measure, the characters of different representations are orthonormal. That's a property we are going to use. And if you extend it to the conformal group, of course, these things get a little bit more complicated, but this is still easy to understand. So this Q to the delta is just the overall conformal weight. And this P factor given here takes care of all the secondaries, because the derivative operator is the del mu in 4 dimension is 1/2 representation of SO4. So the either of 1/2 factors come with their own weights, alpha and beta. So each derivative gives you one mass dimension Q that comes with either alpha beta for up, alpha beta inverse, or up down, and down up, and down down. So this generates all powers of derivatives in a totally symmetric combination. And then comes this character for the Lorentz group for the whatever representation you're looking at. But it has been known, thanks to the work by Franz Dolan and so on, whenever conformal weight is given by 1 plus the J1 plus J2 for a given Lorentz group representation, that which saturates the unitarity bound of the conformal symmetry, then there are these short multiplets which correspond to equation motion. So the chi, the Lorentz character for scalar, of course, is expected to be just 1. But for the free scalar field, you have to remove del squared phi, which correspond to adding minus t squared to this character, which correspond to this numerator in the Hilbert series I mentioned earlier. And same for fermions, you have this alpha plus alpha inverse just for 1/2 zero representation, but you subtract this one, again, to take care of the Dirac equation. And for the field strength of the gauge field, again, this is the piece that you expect from Lorentz symmetry, but you need to subtract two pieces which correspond to equation motion and Bianchi identities. So this takes care of this issue of how to deal with equation motion. And then this presymplectic exponential takes care of the symmetric product of a given representation. And you can show that this, for example, in SU2 case, gives you entire series of totally symmetric product of spin 1/2. Or if you have a fermion, you need to come up with a totally antisymmetric combination. Again, for the simple example of SU2, you can see that antisymmetric combination can give you only up to give you only spin 0 at the end of the day by combining antisymmetric product of two spin 1/2. So this takes care of this infinite powers of every field, either totally symmetrized or either totally antisymmetrized. And this is the slide I have shown you earlier. So this takes care of all fields of a given representation using character under the conformal symmetry as well as the gauge symmetry of arbitrary power, totally symmetrized or totally antisymmetrized, and integration over the gauge group projected down to gauge invariance. Integration over the conformal group picks up the primary. And because the character already encodes information about equation of motion, that's all taken care of as well. So this is the way you can really see how these individual operators can be generated. So what I want to show you is that you can actually code this in a simple mathematical program. All you have to do is to first define all of these Haar measures. And these are the character under conformal group and gauge group for every field in the standard model. And we compute its presymplectic exponentials to allow for arbitrary powers in them, either totally symmetrized or totally antisymmetrized. Then in the end, we expand them in power series in these fields. And for example, in the case of dimension 6, it takes about 10 minutes on Mathematica, but what it spits out is this result, where you can easily identify which term corresponds to how many powers on what field. And the power of t in this expression corresponds to the number of derivatives. So you can clearly read off what operator you can write at a given dimension, and that precisely agree with the counting this Polish group came up with at the end of the day. And on Mathematica, it takes a while, but if you code this in form, dimension 6 is actually, let's see, I don't think this is the right one. So dimension 6 is actually pretty fast. If I run form program, it actually does this presymplectic exponential, and here's the result. This is all set of dimension 6 operators beyond the standard model. And you can even do dimension 8. It takes a little bit longer, but it's still pretty fast. And then you can come up with a complete set of all dimension 8 operators you can add to the standard model in power series of fields and derivatives. And so here they are doing the Haar measure integration, and it's going to come out actually pretty soon. Here we go. There. And this is actually a long list. You can see it's a long list. But nonetheless, I can handle this properly. So after going through this kind of exercise, we can see how many operators exist on a given dimension. And this is the as far as we have gotten so far, up to dimension 15. And this is a log scale. So you can see the number of operators grows exponentially as a function of dimension. And this is a case with only one generation. This is a case of only with 3 generations. But nonetheless, this is now totally automated. So we think we nailed this question of classifying effective operators in a given Lorentz invariant theory. And you have already seen some intriguing connection to the discussion of the amplitudes that had been very much in vogue in the field these days, but we still don't quite understand precise relationships with the classification of operators to the classification of amplitudes. That's an interesting subject we're thinking about now. And we also did a perturbation around this free conformal theory. But if you can apply this method to the already interacting conformal theory and try to classify operators you can add to them, that would be a very interesting subject as well. And we also know effective field theory is not only important in the standard model, but any extensions of physics beyond the standard model, as well as condensed matter, nuclear physics, also density fluctuations, cosmology had been dealt with in effective field theory, and hopefully this kind of formalism can be applied there as well. So that concludes my second part of my talk. And how many minutes do I have left? 20. Oh, that's plenty. And the third subject is, again, building on legacy of Nambu that has to do with pions as pseudo Nambu-Goldstone bosons. We are now trying to use that as the candidate for dark matter. So in the case of dark matter, before I entered the field, that there was already this dominant paradigm called the WIMP, weakly interacting massive particle, because what people call the WIMP miracle. So when you try to understand how much of the dark matter particle is left in the universe today, you consider this process of two dark matter particles annihilating into two standard model particles. And if you take weak coupling, as weak as, let's say, fine structure constant in the standard model, and the weak mass scale, meaning the Higgs mass scale or TeV scale, then if you go through the math, you end up finding the correct abundance. So this is what people call miracle. And especially that the weak scale is where people anticipated some new physics to appear in connection to the naturalness problem of the standard model. This really was encouraging for many of us that the discovery of the new physics may be very imminent. But as we all know, after LHC turned on and many other experimental efforts underway, we still don't see a very concrete signal of any physics at the TeV energy scale. Direct underground detection experiments, LHC, looking at the gamma rays of dual spheroidal galaxies, and the cosmic ray flux shows some contribution of antimatter, which may come from dark annihilation, but is still subject to a lot of controversies. It may be due to other astrophysical sources, and yet no sign of new physics that explains naturalness. So there had been a lot of rethinking going on in the field. The dark matter definitely exists, but some people started to think maybe the naturalness problem is optional instead. So this is sort of the reversed hierarchy from what it used to be. When I entered the field back in the mid-'80s, the idea was that we have to solve these big problems in the standard model and particle physics. That's a naturalness problem. If the solution to the naturalness problem ends up giving you a candidate for dark matter, okay, that's nice. But I guess the evidence for dark matter was not as solid back then. So this was, I guess, regarded as somewhat optional. It's the opposite now. The evidence for dark matter is just irrefutable these days. It's there. It's non-baryonic, something totally new beyond the standard model. We know that now. Naturalness problem, well, at least we haven't seen any sign of the solution to it experimentally. So maybe we should decouple these problems. We need to explain dark matter as its own problem without linking to other problems in particle physics. And maybe we have to decouple these two issues. And for example, the supersymmetry has been the most favorite idea trying to solve the naturalness problem for decades, and that also gives you a good candidate for dark matter. But do we really need really big ideas like supersymmetry to solve the dark matter problem? So at this point, I started to feel like, well, we're trying to kill a fly on the wall, and without using just a swatting on it, we bring a big cannon and shoot at the fly to kill the fly. So that is, in some sense, what I start to feel like supersymmetry. Maybe you don't need as big a tool as supersymmetry or as an exotic tool as supersymmetry to solve the dark matter problem. Perhaps we can solve it with ideas much more familiar to us, such as pseudo-Nambu-Goldstone boson. And when I was starting to think along this line, I happened to listen to a beautiful talk given by Yoni Hochberg and in Berkeley, where she presented this idea called strongly interacting massive particle, rather than weakly interacting massive particle, SIMP, which also gives you a similar level of miracle. So you have seen this WIMP miracle, but there is also SIMP miracle. The difference is that in the case of strongly interacting massive particle, because it's strongly interacting, you may not be able to ignore even higher point interaction like 3 to 2. And this 3 to 2 interaction gives you the reduction in number density of these SIMPs. And again, if you go through the math, for typical strong coupling like 4 pi and strong mass scale like 300 MeV, you end up finding the correct abundance of this particle. So you may say that's the similar level miracle as WIMPs. You take the strong coupling, strong scale, give you the right abundance that have been already discussed by their collaborators. And the analysis is just basically the same thing as what you do with the typical WIMPs. The only thing you change is from 2 to 2 to 3 to 2. Then annihilation cross-section changes. That changes the estimate of the abundance. At the end of the day, you have different dependencies on the temperature and coupling constants. And then this is the end result I told you already. So if you take the mass of these SIMPs to be a few hundred MeV for kind of coupling that's order 1 to 4 pi, you do get the correct abundance. So this is a suggestion that we may use some strongly interacting theory in sub-GeV scale to discuss the candidate for dark matter. And this is where I jumped in. And so the idea is very simple, which is we call the simplest miracle. So it's just the SU2 gauge theory with 4 doublets. That's it. And we expect that this theory leads to chiral condensate. With 4 doublets, you have SU4 flavor symmetry, and SU4 is the same thing as SO6. And this chiral condensate breaks it SO6 down to SO5, or SU4 to SP2, or equivalently. And coset space then is SO6 mod SO5, that's S5. And S5 has non-trivial pi 5 that supports a non-trivial Wess-Zumino term. And therefore, this theory living on SO5, S5 allows for this interaction among pions, which is precisely 5-point, allowing for 3 to 2 annihilation process. And this epsilon tensor really takes care of the invariance on S5. And this is very general. For all kinds of gauge theories, as discussed initially by Witten, SUN gauge theory, when the number of flavors 3 or greater, you again have non-trivial pi 5. For SPN gauge theories, number of flavor 2 or greater, the 2 is the case I discussed on the previous slide, again supports non-trivial pi 5. SON gauge theory, number of flavors 3 or above, again supports non-trivial pi 5, and therefore 5-point interaction among the pions. So all you do is write a copy of QCD, gluons, dark gluons, quarks, dark quarks, and we attribute degenerate masses to them to maximize the flavor symmetry. And when this theory confines, you go to this nonlinear sigma model. You have this usual kinetic term I discussed at length at the beginning of this talk today, and you add this mass term as explicit breaking, and then the Wess-Zumino term. And by expanding this in power of pion fields, you have the usual kinetic term, you have the mass term, you have the interaction terms among them, and then you have this 5-point interaction, which we need for this purpose. Then you can go ahead and do a numerical analysis, and end result is what you expect from this general discussion. So this dash curve tells you the self-interaction among pions occurring due to this dimension 4 terms in the chiral Lagrangian, and we demand that this self-interaction has to be less than something, about square centimeter per gram, which is the limit given from the profile of the dark matter in clusters of galaxies, and also the absence of apparent scattering among dark matter in bullet clusters and so on and so forth. On the other hand, these solid lines correspond to the values you want for the purpose of getting the correct abundance of dark matter. And we require that we are within the validity of the chiral perturbation theory. You want to be below this line. And all 3 requirements can be met in this range of masses for different gauge groups. So again, a few hundred MeV range, which is precisely the mass scale for the ordinary strong interaction we know of, turns out to be right. And the self-scattering, of course, exists because these dark pions have finite size. And I forgot to emphasize that these dark pions are stable because they have this definite flavor quantum numbers, in this case SO5 that's unbroken. And given this is the lightest particle with a non-trivial flavor quantum number, they have to be absolutely stable. So it can be a candidate for dark matter because of that. And you can repeat the analysis not just for SPN theories, but also SUN theories, SON theories. Still, you find a validity range where everything works out, and typically at the 300 MeV mass range for these dark pions. And this self-interaction is actually interesting. So I mentioned this upper limit of the order of square centimeter per gram. And it turns out that this kind of number up against the upper limit can be good because there had been this long-standing problem looking at the dark matter profile in dwarf galaxies where NFW profile expected in the numerical simulation tends to give you rather sharp cuspy structure in the density profile. On the other hand, the observation suggests much more smooth density profile towards the center of dwarf galaxies. And it turns out that small amount of the self-interaction among dark matter particles can basically smooth things out because of the pressure in the gas of dark matter, and that tends to give you a better fit to the observed data in dwarf galaxies. And just the last year, they came out another study of this a system of merging galaxies. You see 4 galaxies here that are actually on the stage just about to merge together. And using weak gravitational lensing, they also mapped out a mass profile in this system. And what they see is that the dark matter is behind the galaxy. So it's actually the galaxy itself, the luminous part, is moving forward towards merger much more quickly than the dark matter that is still sort of left behind. And you can also understand the behavior of this system if dark matter has some kind of self-interaction that gives you basically sort of pressure to keep them away from each other, so that the dark matter joins this merger process a little bit later than the luminous part of the galaxies. And the data says that preferred value of the self-interaction is indeed in this range of square centimeter per gram, but in particle physicist unit, it's about 0.3 barn for 100 MeV mass. And again, you see this is typical parameters of the strong interaction. Barn, that's a typical strong interaction cross-section for 100 MeV particle we are talking about. So it's very intriguing that this might be actually needed at the end of the day. Of course, we don't know yet. But yet another ingredient we need to consider is how they communicate with the rest of us. It turns out that some level of communication is actually needed, because when the dark matter particles go through this 3-to-2 annihilation process to reduce their numbers, 3-to-2 process gives you the 3 times the mass at the initial energy, 2 times the mass as the final state. Of course, 1 part of the mass should be given as a kinetic energy to these final state particles. So the final state dark matter particles is rather fast. Therefore, it's hot. What we want is not hot dark matter. What we want is cold dark matter to build structures like galaxies and clusters. So what that means is that we need to somehow transfer energies or entropies in this dark matter system to the standard model. So we do need some level of communication between the 2 sectors, which is great because at least we can think about how we may be able to discover them. And this is a study Lawrence Hall did a long time ago, that if you have this secluded dark matter system with 3-to-2 annihilation, dark matter system indeed does become very hot compared to standard model. So it doesn't satisfy the usual requirements of the structure formation based on the dark matter hierarchical structure formation. So we do need the entropy transfer. And the simplest thing you can do is to gauge a subgroup of the flavor symmetry in this dark pion, and let the gauge boson kinetically mix to a photon in the standard model. And there's one immediate requirement, that this new photon has to be heavier than this dark pion, so that you can ignore this annihilation process, but that's a very simple limit to satisfy. And here's a possible theory of this. So in the simplest model, we had this SO6 symmetry, and using the mass term, that's already broken to SO5, and we can gauge U1 subgroup of this SO5 and to a new gauge boson, so that pion fields have these charges. And again, this still maintains the stability of these pions. They cannot decay. Even after gauging, you have this SO3 subgroup still totally exact, and this is SO3 triplet. So they don't have charge, but they are still charged under this unbroken SO3 flavor symmetry. These guys don't have non-abelian flavor symmetry, but they do have these U1 charges, which is conserved. So again, they can't decay. And then we just introduce this kinetic mixing between this new photon, the dark photon, to a hypercharged gauge boson in standard model. And obviously, we are talking about rather lightish gauge boson here, and there are all kinds of phenomenological constraints on this new gauge boson, which basically says this mixing has to be small. And here we go. So this vertical axis is the mixing parameter. Horizontal axis is the mass of the vector boson. And you exclude all the things up here in shaded regions from various collider experiments. On the other hand, when epsilon is too small, it doesn't do the purpose of transferring entropy from dark matter sector to the standard model. So you need some level of the coupling here. So that is this region here. You need to exclude this small epsilon region. You need to above this line. But you can still see that there's plenty of parameter space left below the experimental constraints and above our need for the entropy transfer. And the mass has to be bigger than a pion mass. So roughly speaking, this kind of triangle is the viable region of parameter space. So how do we probe this? Well, you might know that this super KKB has just started to turn the beams on. And they are actually expecting an incredible luminosity at the end of the day, 50 inverse Autobahn. That's amazing. And this is a low energy plus or minus machine, but we are talking about rather light dark matter particles. So in principle, this machine can produce dark matter this way. E plus E minus annihilate, produces one photon you can detect. The other photon kinetically mixes into this dark photon that couples to these dark quarks as a final state. And the great thing about E plus E minus machine is that you can measure the invariant mass of this invisible system just by detecting this photon. Because you know the center of mass energy, that's square root S, and you measure this energy of the photon, this is here, the energy of photon is in one-to-one correspondence to the invariant mass squared of this missing system. So just by measuring the energy of the photon, you know what mass of this invisible system is. So first of all, if there is really this additional vector boson, that should show up as a peak in the invariant mass distribution, that's this peak here, that corresponds to the mass of this new gauge boson, which can be seen if it's there in this kind of experiment. But what's more exciting to me is going to the scale, there are these wiggles. What this means is that you have this structural resonances in this dark QCD, which you can pick up experimentally. So again, going back to this idea that when you have the system in this dark sector, which have the resonances, dark rho 1, dark rho 2, and so on, and continuum dark quark pair production, and so on and so forth, that you have a specific resonance structure in this dark QCD, which can show up here. And that again goes back to the legacy of Nambu, where we really struggle to understand the nature of the Lewis resonances as an excitation of a string. And so what we have done in our numerical study is to basically borrow this idea, relying on string theory, using holographic QCD to mock up what kind of the resonance structure might appear in this kind of the general the vector-like gauge theories. And this is one possibility here. So we took this simplest model, SU2 theory with 4 doublets, and we took the parameters that the mass of new gauge boson is 2 GeV, mass of dark pion 300 MeV, and the dark photon coupling is fairly weak, so that it's still consistent with the current limits. And if the lowest dark rho is heavier than twice the dark pion, then of course dark rho decays into pi pi, giving you this relatively sharp peak, followed by higher resonances from radio excitation in this E plus E minus experiment. But given that we tend to have rather relatively large quark mass in this dark sector, maybe the lowest dark rho cannot decay into 2 pions. Maybe it's lighter than that. In that case, this is sort of an extreme example where dark rho is only just 10% heavier than dark pi, then 3 of the first row resonances cannot decay into pi pi, so it annihilates back into dark photon, that mixes back into real photon, decaying to lepton pairs. So you see beautiful peaks of E plus E minus from these decays. So this is a case sort of similar to epsilon spectrum in the real world QCD, and the real world is probably somewhere in between. So you can look for these peaks in the invisible mass spectrum. You can even look for the explicit, the detectable peaks in lepton pairs, and to do the spectroscopy of this dark pion sector as the dark matter sector of the world. And I mentioned this, I relied on holographic QCD. So using this the super KKB experiment, we can extend the sensitivity from the current limit from Babar by basically by 1 order of magnitude and cutting quite a bit into this remaining parameter range. SHIP experiment being talked about the CERN, the new beep number experiment, we don't know if this is ever funded, but if it does, it can also cut into this parameter range down here. And the people are talking about new kinds of direct detection experiments. Because dark matter particle is rather light in this case, usual nuclear recoil is actually not very efficient to pick up the energy deposit in the detector. So people have started to talk about electron recoil, where you rely on electron in a semiconductor in non-conducting band, but the collision with dark matter can knock it up to a conduction band. Then you can sweep it with electric field and detect the presence of these electrons coming from this dark matter reaction. That also cuts into this part of the parameter space. And it doesn't cover the parameter space entirely, but we still seem to have a pretty good chance of getting into it. So this is the conclusion of the third part of my talk. QCD is an old theory, going back to Nambu with pseudo-Nambu Goldstone bosons. And this surprising old theory can become a candidate theory for dark matter. And I would say this is even better than WIMP Miracle. The mass scale is about QCD, coupling is about QCD, and even the theory itself is basically QCD, so this is a miracle cube. And using this idea, we predict that the self-interaction of the dark matter particle is fairly sizable up against the current limit, so it can solve the problem with the dark matter profile in the dwarf galaxies and this new the analysis of merging galaxies. And it has a very rich phenomenology, both in cosmology and particle physics, and we can even think about doing exciting spectroscopy of this dark sector, again, following up on old ideas from Nambu, so he was indeed a great man. Thank you for your attention.
It's a quarter of 12, but we still have one question. The microphone. Analysis of connecting geometry with dynamics seems to be assumed that the basic manifold is one of continuous commuting functions, so the algebra is usual one.
Mm-hmm.
But we know for non-commutative geometric approach, for instance, spontaneous symmetry breaking automatically arises by giving rise to a potential without putting in explicitly the Higgs field and so on.
Mm-hmm.
So I just wonder whether this Nambu's analysis of the algebra and geometry, is it based on basic structure of the manifold?
Yeah, it is. So,
can it be discrete and so on?
Discrete? Yeah, so what I talked about is only the case of continuous symmetries. I did not talk about any discrete symmetries in my talk. But as I have repeatedly emphasized, the case which had been studied for decades, of course, of the Heisenberg model doesn't start with any sort of the Higgs field in the usual sense. But the Cairo-Lagrangian, which I wrote up there, emerges as a consequence of spontaneous symmetry breaking, and indeed described by this continuous homogeneous space. So these homogeneous spaces do emerge, even when you don't explicitly put in some kind of Higgs or Goldstone fields to begin with. Okay, maybe I didn't understand the question. Nati?
There's another subtlety in counting Nambu Goldstone bosons. Can you hear me?
Yeah, that's Mr.
There's another subtlety with counting Nambu Goldstone bosons in relativistic theories,
Uh-huh.
where in a typical example is a brain, some dimensional brain immersed in a higher dimensional space,
Uh-huh.
and then the ghost. You do it and didn't pay attention?
Yeah, I'm paying attention to you, of course. Yeah.
No, I'm asking
brains.
whether I paid attention.
Okay. Go ahead.
Yeah, and there the number of bosons is just the number of transverse directions corresponding to the broken translation generators.
Uh-huh.
But you do not have additional bosons for the broken rotation generators.
Uh-huh.
So I wonder how it fits into your classification.
Yeah, so this is our take on it. So for example, if you think of even an ordinary crystal, you still can apply the same complaint, namely when a liquid crystallizes, it spontaneously breaks the translational invariance, but also breaks the rotational invariance. And we know phonons correspond to the Nambu-Goldstone bosons of spontaneous-Box translational invariance. What happened to rotation? And it turns out that there is a redundancy at the level of operators which can explain this. Namely, simply that the rotation, the orbital momentum L, is x cross p, where p is the generator of translation. So at the level of nodal currents, again, the rotation nodal current is given in terms of the energy momentum tensor. And we know that energy momentum tensor produces a phonon. And when you act this rotation nodal current on the ground state, you expect Nambu-Goldstone boson because of the local symmetry transformation, but it's the same operator basically. So what's going on here is that in general, you can talk about what we call the nodal constraints, namely a certain set of the nodal currents have a linear relationship when they act on the ground state. And when this linear relationship exists, then you have again the reduction in the Nambu-Goldstone bosons because they are not different ones. They're just a redundant description in terms of the different generators. And you can clearly see this example in the ordinary superfluid. So when you have this Ginzburg-Landau theory of, let's say, cold atoms or helium-4, and not only that its expectation value breaks this U1 symmetry of the conserved number, it also spontaneously breaks the Galilean boost. That's yet another space-time symmetry. So you have 3 boost generators. In addition to U1, you have 4 broken symmetries. But in this case, if you just work out the nodal current of the boost generator, it's given by the energy momentum tensor, but it also contains the U1 current because it changes the phase of the Schrödinger field. So if this U1 current creates a Nambu-Goldstone boson, so does this boost current, but again, they're the same thing. So in the case of the brain you talked about, it's also the case where, similar to crystal, translation and rotation are both broken, but they ultimately are given in terms of same operator, and therefore not separate Goldstone bosons. That's our take on it.
Further questions? Thank the speaker.
Okay, thank you.